Okay, let's get started. So first off, some announcements. Is this too loud, by the way, in the back, or for everybody? Just fine? So next week, Tuesday, we'll have our first midterm exam. That's here in this room. Mostly multiple choice, a few sort of short answer questions. Covers all the material that we've discussed so far. I'll ask questions about the book, things that we didn't discuss during the lectures. I'll ask about things that came up during the lectures that you can't find in the book. So that's the midterm. Any question about this upcoming midterm? Yes?
Which scantron?
Ah. That one. Does this look familiar to you? Yeah, so you are responsible for bringing this scantron and a pencil. And needless to say, it's a closed book, the exam. Any other questions? Yes?
Will there be a study guide?
No study guide. However, on Thursday, for those of you who are interested, you can ask any question about the material. We'll have a Q&A session. You don't have to show up. If you feel like you know the material, feel free to not come. But for those of you who are confused about something, you can ask any question about the book or the contents of the lectures on Thursday. And if everybody knows the material, then it could be a very short class on Thursday. So any other, you have a question?
For the free response, is there a word bank? Or like how are the free response questions? Just like
Test your, I haven't made the questions yet, so what should I do? I'll keep it so that a short answer is appropriate.
okay. So it's not like one word response.
It could be the name of a concept,
Okay.
potentially, yes. Yeah. I'll give you a little booklet. So we print out the questions, and you can write on there. Anything else? Yes?
Do you have your lectures recorded? And if you do, where can we access them as an assistant?
Yes. And I should have mentioned this earlier. Is it this one? This is the link that you follow when you access EEE. And notice that here's a link, playlist to lectures. And this leads to a YouTube playlist. So there are 3 lectures there, and there will be, I guess last week's one isn't there yet, but it will be done soon, right? And then today's will be, I'm sure, up soon as well. So yes, you can look at the materials, all the stuff we discussed during class online. Yeah? Anything else? Okay, so today we'll talk about a new chapter from the book about classical conditioning. That's today's section, and operant conditioning next week, Thursday. And so generally this is the study of learning. Now it's already hard to come up with a definition of what we mean by learning. So one aspect of learning is that there's a long-lasting change. So any sort of short-term aspects of cognition, that's really not about learning. It should be something long-lasting, something fairly on a long temporal scale. It should involve knowledge and behavior, not just some change in some physical state like fatigue, but something in your mind should be altered, and it should be as a result of experience, right? You're learning about something, you're learning about the world. Now, there are different traditions in psychology to study learning. And here, the two biggest divides in psychology, the divide between behaviorism in the early 20th century and cognitivism, essentially the approach we take now, today, from the 1950s to present. So in behaviorism, the focus was on very simple learning mechanisms. Mechanisms that can be applied to humans as well as animals, that could be applied to just a variety of context conditions. The focus here was on animal studies. The idea was that animals are more easily controlled. You can more easily do experiments, fewer ethical issues to worry about, perhaps. And most importantly, animals don't have sort of a rich knowledge background that might potentially contaminate the results. At least that was the idea behind behaviorism. And so behaviorists, some of who we will talk about today, they introduced stimulus-response theories. They really boil down all of learning to the learning of associations between stimulus and response. And they were kind of extreme in that way. They made a claim, a very bold claim, that all of learning, including very complex behaviors, were due to just simple associations. Now, a lot of the stuff that we'll talk about today is extremely useful. It has real-world applications, and it's based on behaviorism. From behaviorist research, we know how to deal with phobias and potentially extinguish certain phobias. We know how to deal with problems with drug addiction, how to perhaps prevent overdose deaths. But clearly behaviorism is too limited. So in the 1950s, people started to complain, saying that learning is surely much more complex than just stimulus-response relationships. The learning of a language can't just be learning of association between words that you hear, or words that you hear and some response in the environment. It has to be involve representations, it has to involve more complex mental processes. One example of a mental model or an information processing model was that modal memory model that we discussed, I think 2 weeks ago. That's an example of the kind of model that came up during the cognitivism era. And also cognitivists, they focus much more on human learning as opposed to animal learning. So there's a number of forms of learning that we'll go into today. The simplest form of learning just relates to a single stimulus, and it's habituation. So it turns out that a response to a stimulus will decline if the stimulus is repeated over and over again. We are learning which things are interesting and which things are not interesting. Things that repeat themselves over and over in the environment are probably less interesting and probably less important to pay attention to. Things that are novel are things that will automatically draw our attention in terms of eye movements. It will capture our attention. So the polar opposite of habituation is dishabituation. So whenever you present something new, that can lead to an increase in responsiveness. Now that is, let's see, oh, here's the video. That is very useful as a way to study infant cognition. So pre-verbal infants, let's say we're talking about an infant that's 9 months old, it's very difficult to do research with humans at that age. You can't quite ask questions like, what do you know, what don't you know? But you can do clever experiments that involve the principle of habituation. You can show a certain stimulus, and if you show a certain stimulus over and over again, the infant will habituate. Now, how can you measure that? You can measure looking time. If the infant thinks it's interesting, it will look more often, have more eye gazes towards the object. But will gradually habituate. Now, if you now introduce a new object, and the infant is still bored, and will still not sort of look, or will look as much as it was looking before, then you know that the infant has not discriminated between object 2, this new object, and object 1. And therefore you can draw conclusions that the infant is unable to draw a distinction between those two objects. If, on the other hand, you have a new object and you see a dishabituation finding, so all of a sudden looking times increase, then you know that the infant is able to discriminate between these two objects, and that can be useful to draw conclusions about what things infants can process. So infants that are 2-month-old, they might not be able to discriminate very well between certain faces. Let's say the face of the mother and the face of the father. But a 4-month infant is probably able to do this, and might habituate to the mother's face, but might quickly dishabituate to the father's face. And then you know that there's a distinction, a mental distinction in the infant. So here's a little example video of how this paradigm might work. And this is very tricky research. You have to carefully monitor the infant's eyes, see where it's looking. Let's see, is the audio on? So it's becoming gradually more bored. So you get the idea. And now you present something novel, and all of a sudden you get the interest back of the infant. Now, a more interesting form of learning is about relationships between stimuli. And there are two forms of associative learning. One is classical conditioning, and the other is operant conditioning. So classical conditioning is about the learning of reflexive responses to new stimuli. So classical conditioning started based on the seminal research by Pavlov with his dogs. So Pavlov did not intend to study human learning or animal learning. He was a physiologist. He studied the digestive tract of animals. But to his amazement, he discovered that the dogs were learning all kinds of things in anticipation of food. The sight of the animal caretaker, or certain sounds that would precede the presentation of food. So I want to show you a video that gives you a sense of the setup of how Pavlov did his experiments.
Pavlov's aim was to discover what caused saliva to flow. He rerouted the salivary ducts to the outside of his dog's cheek so that he could collect and measure the spittle. Perhaps he thought the production of saliva might be the result of a fixed nervous reflex, like a knee jerk. After taking many measurements of spittle, he confirmed that the dogs drooled automatically when their tongues touched food. He called the response the salivation reflex. But his work started to run into trouble. As his dogs became familiar with the experimental routine, they started to fill their cheek tubes before Pavlov had a chance to stimulate their tongues. The dogs were learning to anticipate food. Pavlov tried a new technique. He erected screens so that the dogs couldn't see what was going on. Before passing meat through the hatch, he introduced a stimulus that was totally unrelated to feeding. A ticking metronome. At first, the dog dripped saliva into its cheek tube only when the food appeared. But after a number of trials, the dog began to connect the ticking with the arrival of meat. Soon the sound alone made the dog drool. Eventually, the dog salivated as much to the ticking itself as it did originally to the presentation of food.
Come there! It is to that. Stay away.
He called this new response the conditioned reflex. Whatever the stimulus, his dogs could soon be conditioned to produce saliva. Pavlov believed that he had discovered how animals learn, even in the wild.
All right, so this gives you a bit of a sense of how he did his experiments. So any questions about that setup? Okay, so here's a summary of the finding and basically a pictorial description of the classical conditioning paradigm. So before training, there's the unconditioned stimulus and an unconditioned response, and there's a reflex where salivation is a reflexive response to food in the mouth. Right, so the notation used here is US, unconditioned stimulus, leads to an unconditioned response, salivation. That's just already there, established, perhaps evolutionary. No training is necessary. Now, if you pair, before any training, a tone or some other stimulus, or if you just present a tone, I should say, that's the conditioned stimulus, before training, there's no response. Now, during training, you present this CS, the tone, with the unconditioned stimulus, the food in the mouth. And how you do this pairing is very important. Let's say that the CS precedes the US. So the tone is presented a little bit before the food in the mouth is presented. Either at the same time or a little bit before. We'll go into the exact temporal relationship in a few slides. But that establishes an association between the tone and the food. Then after training, this is the classical conditioning result, you get the same reflexive response. The US still leads to the salivation response. That hasn't changed at all. But now the tone by itself, without any presentation of food, can also lead to the salivation response. So it's as if the animal has learned this association between the conditioned stimulus and the unconditioned stimulus, or alternatively between the conditioned stimulus and the response. Now, as we'll see, this response, the learned response, can be very similar to the unconditioned response, but it can also be very different. But this, in a nutshell, is classical conditioning. Now, there's a whole lot of details that are very interesting to study. One is about the temporal, the time course of learning. Now, learning takes time. It takes some pairings of the CS and US for learning to evoke a conditioned response. So in this sort of hypothetical curve, so you have time going horizontally, and if you do this pairing, over time, the animal, the dog, let's say, learns that the food will arrive when a tone is presented. Now, what happens when the CS is presented, but food no longer arrives? So that's called the extinction phase in classical conditioning. So the result is that if the CS presented without the unconditioned stimulus, you see extinction. Gradually the animal learns that that association is no longer true. But again, that takes some time. Now here's the curious result. If you now take a break from the experiment, come back, and you present that tone again that seemed to be extinguished after this extinction phase, what you see is spontaneous recovery. It's as if the dog believes that the food might be coming after all when you have the tone presented, or the metronome. And that's a somewhat curious finding. Then, if you then have this extinction phase where you just present the CS alone, just tones and nothing else, you again extinguish this, this whatever recovery was presented here during this phase. And you need to have multiple extinction phases for the response to really disappear. But there's still a question. So if spontaneous recovery does not occur anymore, has the association been completely erased, or is there still some residual knowledge somewhere in the organism that there is the potential of a relationship between the tone and the food? And it turns out that even if you see complete extinction, the animal still somewhere has some residual knowledge of this association between the stimulus and the unconditioned stimulus, because it takes you less trials to sort of recondition the animal. Fewer trials are needed to reestablish the salivation response. So what's important here is that the extinction happens in a specific context. Right? So you present a CS in a specific context, and if there's no food, the dog might learn, I'm getting no food in this particular condition, in this, when at this time of day with this person present. And so it's learning, okay, it's not happening now. During spontaneous recovery, the dog might believe, okay, maybe it will happen now in this different context, different point in time, different spatial context. So to truly extinguish a response, you need to train in very different contexts. And that has consequences for how you deal with learned fears. People that have a fear of heights or fear of spiders or snakes, if you try to extinguish this response by presenting the fearful stimulus, let's say it's the spider or the snake, but you make sure that the people feel safe, right? There's no unconditioned stimulus present. Then you can extinguish this fear response, but only in that particular context. You're learning, like, I'm safe now, at this point in time, with this particular spider or snake. But in a different context, you might see spontaneous recovery, where people are again fearful. It's because you need to extinguish these responses under many different circumstances. Does that make sense? Yes?
That tied back to memory and how you can implement false memories. Is there a correlation between that, where you can have someone believe that something should happen based on a certain event, and then over time they may forget it? However, if you give them that same response, they would.
What is the response in this case?
Or the unconditional response would be to have fear or memory of something being something they don't want.
Yeah. I don't quite see the connection yet.
Okay. So I guess my whole point is like how we're talking about how the spontaneous recovery occurs.
Yes.
Of the conditioned response.
Yes.
When we tie it back to memory, is there a plausible connection there where they're actually remembering the responses there, or?
So I guess the point is, so clearly this is a form of memory, right? And this is more a form of implicit memory than explicit memory. That's one distinction. And what the animal is learning is sometimes it's very specific about this stimulus. Right now, and this other stimulus right now, in this context. Sometimes the animal or human can generalize beyond that. Yes? Okay. So there's a lot of research with animals, and there are obvious reasons why we have to be careful in working with humans. So a lot of classical conditioning involves reflexes, fear responses, and you have to be very careful with training people to be fearful, or even preventing them to be fearful of some things, because you can do long-lasting damage. So Watson is an infamous researcher. He's one of those behaviorists that had fewer sort of ethical constraints, so to speak. So he did some experiments with young infants where he exposed them to some innocent stimuli and then trained them, he exposed them to some fearful stimuli where the infant learned the association between the innocent stimulus and the fearful stimulus. So let's watch.
In the early part of the 20th century, psychologists John Watson and Rosalie Rayner set out to teach a baby boy called Little Albert to fear white rats using the principle of classical conditioning. This is a film of their work. The film shows several phases of their study. First, as you see here, the investigators demonstrated that prior to conditioning, Little Albert had no fears of any animals, including, of course, white rats.
So this is before training, where he likes the rat.
Watson and Rayner then sought to teach Albert to fear white rats through classical conditioning. In the conditioning phase of the study, which was not filmed, the investigators struck a steel bar with a hammer whenever Albert reached for a rat, making a very loud noise that greatly upset and frightened Albert. After 6 such pairings of the loud noise and the rat, it was believed that the boy had been conditioned to fear white rats. That is, Albert was now expected to react fearfully to white rats, whether the rats were paired with loud noises or not. In this next film sequence, we see Albert interacting with a white rat after the conditioning process. The investigators believed that the child's reaction during this trial demonstrated his newly acquired fear of white rats. Finally, the investigators expected that little Albert's conditioned fear of white rats would generalize to stimuli that were similar in key ways to a white rat. In this film segment, the child now also reacted fearfully to similar objects such as a rabbit, a dog, a furry object, and a white mask worn by Watson himself.
All right, well, you get the idea. So poor little Albert. This is why nowadays, if you do any experiment with people, you need to get approval from the IRB, which is a good thing before you do these crazy experiments. Now, one good outcome, I guess, little salient detail here. Watson, he had an affair with his grad student, shown in on the right, which is a big no-no in any university, so he was relieved from his duties. Unfortunately, little Albert, he was in a hospital situation. And he moved on to a different hospital, and nobody ever sort of dealt with his fear response, so he might have had this fearful response, unfortunately, for the rest of his life. Yeah. So you have to be very careful. So any question about that? And this, by the way, was just, I believe it was only 10 loud hammer noises. Is it 6? Okay, I read, okay, 6. 6 pairings with the white rat. That was sufficient to develop this sort of deep learned response that generalized to, a variety of other fluffy things, including a Santa beard. Okay, so there's a number of these US-UR pairings you could study. Pavlov studied the food salivation response. You can study electric shocks, pain reaction, learned food aversions. Those are particularly strong. Or very simple ones like puffs of air and how they can evoke an eyeblink response. Now, all of this is implicit learning. This is using routes that are very different from the explicit learning route, explicit memory route that we discussed the last lecture. And these are different sort of brain areas involved. It's very involuntary. When you can train yourself on these, with these stimulus-response relationships, and it's hard to control it. So here's one rare video that I found where a person is learning an eyeblink response in response to, I think, some hammer on a desk. And this is outside sort of conscious control. So let's see this video.
Okay, as you can see, Howard has got a straw pointing at his eye, and via this a long set of straws that are taped together comes to a blue bulb on my desk over here. And if I squeeze the ball, Howard has to blink. And I guess let's go to our split screen here. Because the air is puffing into his eye. And we've got him turned in such a way that he can't see the blue ball. Now, from classical conditioning, we could expect that since what we have here is a reflex, that whenever the air puffs, that he should blink, right? Really has no choice over that. But let's suppose, and this may take more coordination than I have, little Jerry Ford, President Ford, trying to walk and chew gum at the same time. And I'm going to try and use a pencil tap here and pair that with the puff of air enough times, and then let's eventually see what happens. See what happened?
All right, you get the idea. So this training, by the way, this is probably happening in the cerebellum. There's some circuitry that has this very fast training where this learning takes place, and this works even for people, right? So this guy might reflexively blink whenever he hears a pencil tap. That might go on for a long time. Okay, so there's a number of concepts and phenomena related to classical conditioning. So let's go through these. So there's second order conditioning, generalization, discrimination, temporal ordering, contingency, and blocking. Okay, so first, second order conditioning. So you can study not just single associations, but also chains of associations. And you can train people to learn these chains. So that's what second order conditioning is about. So if you first present a training phase where the food is paired with the sound, so the US is paired with one conditioned stimulus, that might establish this relationship, this association. Now if you, in the second phase, have another stimulus, let's say CS2, let's say it's light, and that precedes the first conditioned stimulus, the sound, and very important, it's followed by no food, so there's no US here, then now this person can learn that the light is indicative of the sound coming. Then in the third phase, the testing phase, if you now present light by itself, that can actually elicit the conditioned response. Although that response is not quite as strong as if you presented the first conditioned stimulus. So a chain is learned between different stimuli. And behaviorists thought that complex behaviors can be trained in this way. So it seems very difficult to go from reflexive behaviors to very complex things like language. But this is how they envisioned that this would work. That you set up this very complex chain or web of stimuli and learning associations between them. The other concept is generalization. So we've seen with little Albert. Little Albert was trained to be afraid of white rats, but he also became afraid of other furry things, including Santa beards. So that's an example of generalization. Now in experiments, you can establish a generalization gradient. You can see how the response sort of levels off if you move further and further away from the preferred stimulus. In this experiment, a 1200 hertz tone was paired with the unconditioned stimulus. I think it was an electric shock. And not surprisingly, if you present the 1200 hertz tone, the exact same tone at test, you get a pretty good conditioned response. But if you present somewhat higher pitch tones or lower pitch tones, you get a somewhat lower response. And how this curve sort of levels off as a function of the stimulus and the distance from the original stimulus, that's called the generalization gradient. So that indicates sort of how far a person or an animal is willing to generalize and believe that the conditioned response is related to this new stimulus. Does that make sense? Okay, so here's a tricky thing that when it comes to temporal ordering. It's very important that the CS and the US are presented in the correct temporal sequence. If you present, let's say the tone, let's say that that's the CS, that's shown in green here. If you present the tone after the unconditioned stimulus, let's say it's a shock, no learning takes place. So in this graph, the stimulus interval is shown, so it's the delay between the CS and US. If you have negative numbers, that means that the CS is arriving after the US. And the vertical axis shows how much of a response there is. So here there's very little response, or actually less of a response when you have backwards pairing. So the animal is not learning anything if the conditioned stimulus arrives after the unconditioned stimulus. If you do simultaneous pairing, if you have the tone and the shock at the same time, then also very little learning takes place. You saw in the video with the eyeblink, the pencil tap preceded the delivery of the puff of air. So it was not simultaneous. And when you have this forward pairing, so we hear the pencil tap preceded the puff of air, or the tone precedes the shock, then you get the strongest conditioned response. And it varies from stimulus to stimulus, but it's about half a second leads to the optimal delay. If it's shorter than that, the association is not very strong. If it's very long, the association is also not very strong. So temporal ordering is one key ingredient to successful associative learning. Now here's the trickiest concept. That's probably the most confusing to you. The concept of contingency. The primary factor in establishing an association is a probabilistic relationship between the US and the CS. The CS should be informative about the arrival of the US. And it should be informative in a sort of probabilistic fashion. Now, what does that mean? So let's give an example. Suppose there are 200 trials. 60 trials, you present the CS and the US follows, or you present the CS and 40 trials, no US follows. So it's more likely that the US follows after this conditioned stimulus than not. Now that by itself is not sufficient to trigger learning. It's also important what happens when you don't present the CS. So in this particular example, there are also 60 trials where the US follows after no CS was present. And here there's no contingency. The arrival of the CS does not give you information about whether the US follows or not. And therefore no conditioning occurs. In the bottom example, the numbers look very similar, but here there is a contingency between the CS and US. So now it is slightly more likely when the CS arrives that the US arrives. But it's probabilistic, right? It's 6 out of 10 times, 60% chance when the CS is present, 40% chance when the CS is not present. Here conditioning does take place. So conditioning does occur. So you have to look at the full pattern of the data. It's not just the number of times that the US is paired with the CS, that's not sufficient. You have to look at the contingency pattern, the whole table. Does that make sense? Is there any question about this? So here's another tricky example. Suppose you have a stimulus that's always on. So in Pavlov's experiments, there's a light maybe that's always on. There's a door that's always there. There's a wall that's always there. That surely can't be learned, that's relevant. So if the food arrives and the wall is always there, the food arrives and the door is always there, that doesn't seem very informative. So if you look at this example in this contingency table, if you have no CS present, so you have zeros in the bottom row, and you have, let's say the CS, when the CS is present and the CS is always present, 50% of the time US occurs and 50% it does not, there's no learning here that takes place. Again, there's no contingency. The key here is what happens with the numbers off the diagonal. If this number and that number is high, then you have a contingency. So when it's more likely that the US arrives when the CS arrives and less likely when the CS is not there. That's the key. It's hard to explain this in words, but does that conceptually make sense? Okay. Here's another tricky thing. This looks a little bit like second order conditioning, but this leads to very different effects. So this is called blocking. And this shows that what matters here is the new information that's provided by a stimulus. Suppose in this paradigm you have one stimulus that's paired with the US. Let's say it's a tone paired with a shock. In the second training phase, you introduce a new stimulus, CS2. Let's say it's light. So you now have, again, the tone with the shock, but light is introduced. And let's say that light is presented at the exact same time as the tone. Now you might think, intuitively, that the person or animal might learn this association between tone and shock and between light and shock, because there appears to be this contingency. But the result is that if you now present the light by itself, even though it was paired with the shock, there's no learning that took place for this second stimulus. And that's a curious finding. Why is that? Because of blocking. During this second phase, this light provided no new information about this arrival of the shock. The shock was already perfectly predictable by the arrival of the tone. So contingency also is not quite sufficient for learning. It's contingency plus it should be something new that's presented by the stimulus. Light here doesn't present any new information, so therefore there's no association learned between light and shock. So the stimulus should provide new and independent information. That's the key finding in this blocking paradigm. Now, the reason why this is tricky, this looks very much like second-order conditioning, right? In second-order conditioning, you learn first one association. In the training phase, you introduce this new stimulus. You have a CS1 and a CS2, and voila, in second-order conditioning, you do have this generalization from the second stimulus to the conditioned response. Now, what's different? The difference here is that in this blocking paradigm, you still present the US during this second training phase. The other major difference is that in blocking, you present CS1 and CS2 at the exact same time. The tone and the light is presented at the exact same time, and therefore, the light does not provide any independent new information about the US. In second-order conditioning, you present the light, the new stimulus, before the tone, and no US. So there the light can be predictive of the tone. And there you do get generalization. Does that make sense? Okay. Now, often these conditioned responses, they can be very similar to the unconditioned response. So your fear response to some new stimulus might be very similar to the fear response of the original sort of evolutionary response. But sometimes your conditioned response might be very, very different from the unconditioned response. It might be more like a preparatory response that's adaptive to the organism. For example, if you shock a rat, the heart rate will go up and the animal will try to escape, will jump up. But the conditioned response, let's say there's a tone that the animal has learned to pair with the shock, the tone might actually lower the heart rate and might freeze the rat in place, which could be an adaptive response. Your response to caffeine, your learned response to caffeine, that might be different from the actual effects of caffeine. Athletes that are anticipating intense physical activity, they might get the pre-game jitters. And this might be because the body is releasing blood sugars in response or in anticipation of intense physical activity and preparing for this physical activity. Now, in other cases, the preparation could be of the polar opposite of the unconditioned response. It might actually be compensatory response. For example, with drug addiction, Your response to the drug might elevate your mood. Your conditioned response, all the things you learn in association with the drugs, the needles, the place where you take drugs, let's say, if we talk about heroin users, that might actually lower or depress your mood. And the body might be learning to prepare itself for the oncoming drug and try to sort of compensate for this, for the effect of the drug. There's an amazing experiment with rats in ice boxes, where rats are put in these freezing ice boxes, and so they learn that ice boxes are cold, and they have this reflex where the body of the rat is doing all it can to elevate its temperature. Now, if you put the rat in an ice box, in this ice box, but now you don't turn the ice box on, what you find is this compensatory response where the rat actually increases its body temperature. That's because the rat has learned to fight the cold in the ice box, and now it just sees the ice box again and tries to compensate for the oncoming cold. And I think perhaps the most amazing finding is that the compensatory responses might explain why some animals or people die in certain conditions but not others under drug or when an overdose of drugs is delivered. So in this experiment, rats were given heroin, and they gradually developed a tolerance for the heroin. Right? So you learn this compensatory response, your body is fighting the effects of the drug, and over time you're becoming better at this compensatory response. So you can deal with higher and higher amounts of the drug. So these rats that learned this tolerance, they were now given an overdose, twice the amount of the drug as they were given before. And when these rats were in the same setting, let's say it's the same sort of cage that they were in, the same other animals that they were paired with, about 65% of them died because of the overdose. But fewer of these rats died when they were in the same physical context than when they were in this different context. So when they were put in a different cage, a different physical setting, different time, more of these rats died, even though they got the same amount of drug. And the explanation is that this compensatory response didn't kick in. They didn't have this learned response, this compensatory response, because the setting was sufficiently different. And this might explain why heroin addicts can sometimes die if they are placed in a novel surrounding. Their usual compensatory response, which allows them to survive dealing with these high amounts of toxic drugs, doesn't kick in because they're in a new environment. The body hasn't learned that sort of association yet. And so it can't deal with with the effects of the drug, and therefore people can die. So that's one explanation for these seemingly puzzling deaths of heroin addicts in these new environments. Okay, so that's it for today. We'll see each other on a Q&A session on Thursday.